So this is fun. I recorded this whole video and it was just my face. So you didn't get to see any of the notes. So here we are. I hope I don't miss anything. Ugh. I hate recording back to back because I always wind up missing stuff. So anyways, enough nonsense. We are starting this lesson, which is on nuclear reactions. There are 4 types of nuclear reactions, and the very first type is called a natural transmutation. So it is called natural because nature handles it. It happens on its own. It's spontaneous. And it's called a transmutation because one element is mutating into another. Trans means across. So like transport. So we are moving from one element to another element. This example here is an example of carbon-14, which is how archaeologists date old dead stuff. This is how we know how long ago dinosaurs lived. We know how old, like crazy old trees are, like the things that are like 5,000 years old. We can also figure out if we like dig up Neanderthals, which are like some of the earliest people, we can dig them up, not we, but archaeologists, and they can figure out how long ago they lived. And all of that is with carbon-14. Everybody who is alive, you, me, your dog, a plant, they all have carbon-14 in them, small amounts. And depending on how much is left, scientists can figure out how long ago that thing was living, because once something dies, it starts, there's no more new carbon being introduced because it's not breathing anymore. It's not eating or getting any nutrients anymore. So the carbon that's in there is the carbon that's in there. And they do that by calculating with half-lives that we will get to later. In this case, the carbon-14 is breaking down into nitrogen-14, which is absolutely stable. And this baby is not so stable. And it does this by giving off beta particles. Remember beta, you can do the B with the long tail, or you can write E because it's basically the same as an electron. Why did I write E equals mc squared? Oh, because Einstein is Albert Einstein, you know, like the famous guy, maybe the smartest man ever, at least on paper. There's probably other people who were smarter who just didn't, become very well known. He wrote down the equation for us, E equals mc squared. This basically tells us that E for energy is equal to mass times the speed of light squared, which essentially means that all matter, all of it, is compressed energy. You take matter and you can essentially squeeze it and then it becomes energy. I mean, opposite. Take energy, squeeze it, it becomes matter. So this is how we can convert one form of matter to another, is because of this energy component. Before that, we were trusting entirely the law of conservation. Law of conservation is still true. It's just phrased a tiny bit different. It used to say like matter has to be conserved and energy has to be conserved. And now we think of it like matter and energy are kind of like this weird little fluid thing. And we can bounce between one and the other, but in total, there's conservation. The next thing we have is an artificial transmutation, which I'm going to shrink this a little bit because the bubble is giving me trouble today. In this case, we have a nucleus, and we are going to bombard it, is the word that they like to use, with smaller particles. So here in this example, this aluminum is being bombarded with alpha particles. We can also do this with neutrons, which is why this little neutron is down here. Atomic number 0, mass number of 1. And this is what happens like in a particle accelerator. You would have smaller atoms that get bombarded with even smaller particles, and then those are going to sometimes stick to the atom. So in this case, the aluminum and the alpha particle are sticking together and giving us a phosphorus. This is actually how they made most of the elements, like the big heavy ones, like greater than 100, like all those radioactive guys at the end of the periodic table. Those don't exist like in nature. They're only made by humans, and they make them with an artificial transmutation where they take like a big atom, and then they'll launch a particle at it and hope that it sticks. And a lot of those elements took a lot of practice, because sometimes they would stick, but other times they would hit the atom and the atom would break. Atoms are pretty delicate. These things are driving me crazy. So that's an artificial transmutation in a nutshell. Practical uses for them, I don't really know. Honestly, I think it's just to explore nature's limits. Next thing we have is fission, and fission is how we make nuclear power. There are some parts of America that function on nuclear power. I know a lot of France, like 85 to 90% of France's power comes from nuclear reactions. If you have HBO and you watched the Chernobyl documentary type series thing, that was about a nuclear power plant. Who else? Japan. They had a nuclear meltdown in 2013, I think it was. They had a power plant. They had a power plant, and Japan is an island, so they're like in the ocean. They're surrounded by the ocean, and there was a earthquake in the middle of the ocean that caused a tsunami that washed up on Japan and caused a nuclear meltdown, and it was like kind of intense. So that is nuclear fusion. They'll use uranium or some other like really hefty element. Plutonium sometimes, those things like in the lower 90s. And what happens is they will take a neutron or some other smaller particle and, they'll take a smaller particle and then try to break the uranium. And then what happens is that one uranium will fly across the reaction vessel and hit another uranium and get it to like pop open. And what happens is it breaks down into these smaller, like mid-range elements. And that is what I'm trying to demo for you right here. I would love to do this in our classroom. We're going to imagine that each one of these little triangle things is a uranium. They are super delicate in that they love to pop open. And I'm going to stop here because I'm ready. We are going to take, see, it does this, and then you just like tap it and it pops open. You see that? So this is going to pop, and then it's going to hit one of these, and then that's going to pop, and it causes a chain reaction, but it happens really fast. So it's popping in my hand. So let's imagine this is a neutron. Oh my God. This gets me so, especially because it's so close to me. Here we go. Ready? That's what happens. That is a fission reaction, and that is how we get nuclear power. All of those, except one, exploded all at once, and that is why you only need a small amount of nuclear material to get a lot of energy. It's because of this breakdown. And then sometimes these products, the krypton or the barium, I don't know about these in particular, but sometimes this stuff, which is called nuclear waste, can go into its own nuclear reaction and then get used again. So that's another reason why people are proponents of nuclear power, is because for the amount of material you need, you get a lot of energy, and sometimes you can recycle the waste and use it again. And then the downside, obviously, is that this is not really healthy. We're not really sure. I mean, we do know effects of radiation for sure, but there's a lot of unknown to it. And then there's also a lot of danger. If things go wrong, they go very wrong. So it's something that some parts of the world use and other parts don't, but I think it's something that we should consider. Now, and that's really just because the fossil fuels are destroying the atmosphere, but that's something else entirely. This game, in case you're interested, is called Boom Blastics. It's like reverse Jenga. It's a lot of fun, but also very nerve-wracking. The last type of nuclear reaction is called fusion. And fusion essentially is what happens inside of a star. So we would have our sun, for instance, is made out of hydrogen and helium. And what happens inside the sun is that we have I don't know if you knew this, we have a giant nuclear reaction happening in the sky. and it emits radiation. It emits all types of radiation, including UV radiation, which is how you get a suntan or how I get my freckles. And if you get too much UV radiation, it's not healthy for you. It can cause skin cancer or other things, which is not healthy for you. But a little bit is healthy. A little bit can help you get some vitamin D. Helps you absorb vitamin D. And you get vitamin D from some foods that you eat. So here's fusion. We have, in this case, a hydrogen and a helium, and they are literally fusing together to make a lithium. This is what happens in stars. Our star, or the sun, uses hydrogen and helium, and then there's other stars and other suns. A sun is just like another name for a star, basically. They will fuse other elements. So some of them are fusing carbon as a common one. Some of them fuse iron, which usually means it's towards the end of its life. But these reactions, because the stars and the suns are so big, these reactions will happen for billions of years. And if you think of the amount of energy that our sun gives off, and for it to be going for billions of years, it's kind of crazy. And the end of our sun's life is nowhere in sight. Our sun is probably going to last a few more billion years. Obviously, scientists are estimating, but nuclear gives you a lot of bang for your buck, but it's also super dangerous. So you got to weigh pros and cons. But this is stars. This one is nuclear reactions, like nuclear power. Then for artificial transmutation, come on, give me a new page. Go back to the page. Oh, goodness. Then we have, and now this is delayed, of course, a natural transmutation where nature is breaking down elements and turning them into safer things. And then here we have an artificial transmutation, which is what happens in a particle accelerator. And that's that. Those are your 4 types of nuclear reactions. So if you have any questions, leave a comment. I will do my best to get back to you. And that is all. Have a great day.